Hi there, Mr. Holcomb here with another episode of The Math Behind the Modules. Welcome to Lesson 18, Analyzing Residuals. So we're talking more about residuals in this lesson. Classwork. The previous lesson shows that when data is fitted to a line, a scatter plot with a curved pattern produces a residual plot that shows a clear pattern. You also saw that when a line is fit, a scatter plot where the points show a straight line pattern results in a residual plot where the points are randomly scattered. So example 1 says the relevance of the pattern in the residual plot. Our previous findings are summarized in the plot below. So here we have that looks linear. So if I were to take and draw a fit line, it might go something like this. You might think it is linear and just stop at that and say, oh, that's got a positive, strong relationship and it's linear. But then when you look at the residual plot, things change. This residual plot has a pattern. So when a residual plot has a pattern like this parabola, this would probably have a better fit, not linear, but more so quadratic. So this is definitely, it may look linear when you originally look at it, but in all actuality, there is a curve going on here and something like that happening. So if the trend continues, you would expect this to continue downward because the residual plot has a pattern. Hopefully that makes sense now. And now we're going to look at the next one. Again, this may look linear at first glance, but then when we look at the residual plot, this residual plot has a more pronounced curve going this way. So then after thinking this would be a linear regression, looking at the residual plot may change your mind and you would go back and say, no, that wasn't linear, it's something else. It's exponential or quadratic. Okay, but then the last one also appears to be linear. So now let me do a straight line like I was doing before. So let me pick a line, make it green. And so this one looks like that. But then when I go to look at the residual plot, there is no pattern here. It just seems scattered. There's a bunch of points above, a bunch of points below. I cannot draw a parabola this way. I can't draw a parabola this way like these. This just seems like a random scatter. And that's what you want if you're looking for a linear pattern. You don't want a pattern in your residual when you have a linear regression. Okay, page 2. First question says, what does it mean when there's a curved pattern in the residual plot? Okay, kind of a lengthy answer. A curved pattern in the residual plot indicates that the relationship would be better described by a nonlinear function. When you see a curved pattern in the residual plot, you should investigate nonlinear models rather than using a line or model to describe the relationship. See the first two scatter plots and residual plots in the figure above, which show a curved pattern in both scatter plot and the residual plot. Okay, next question. What does it mean when the points in the residual plot appear to be scattered at random with no visible pattern? So that was like our last example on the previous page, and that there would be a linear pattern. Okay, so when the relationship is approximately linear, the points in the residual plot are scattered at random around the horizontal line at 0. This indicates that a linear model is an appropriate way to describe the relationship. Again, like I said, see the third scatter plot and residual plot in the figures above, which shows a linear pattern in the scatter plot and no pattern in the residual plot. Okay, so moving on, it says, why not just look at the scatter plot of the original data set? Why was the residual plot necessary? The next example answers these questions. So example 2 says, why do you need the residual plot? The temperature in degrees Fahrenheit was measured at various altitudes. The altitude in thousands of feet will be our x-axis, above LA. The scatter plot below seems to show a linear straight line relationship between these two quantities. Okay, so we'll take a look at this. Okay, so I just had to do a bunch of screenshots and rearrange these pages so we could look at these graphs on the same page. And I lost a little bit of clarity here. The resolution's been tarnished, if you will. But anyway, here's the next page. And the data source, core math tools, altitude, thousands of feet, x-axis, temperature, degrees, Fahrenheit, y-axis. This appears to be linear. I do see kind of a bit of a curve there, but it does appear kind of linear. But then when we look at the residual plot, look at this plot. It's almost like a parabola or maybe even absolute value. And it says here there is a clear curve in the residual plot. So what appeared to be a linear relationship in the original scatter plot was in fact a nonlinear relationship. How did the residual plot result from the original scatter plot? Okay, so the residuals are the vertical deviations from the least squares line in the original scatter plot. Because of the change of scale, tiny vertical deviations can be shown as much larger distances from the zero line in the residual plot. Therefore, a very subtle curvature in the original relationship can be seen more clearly in the residual plot. This is why you draw residual plots. Exercise 1 through 3 says volume and temperature. Water expands as it heats. Researchers measure the volume in milliliters of water at various temperatures. The results are shown below. So they're giving us an X and Y table. Okay, page 4 brings us to this problem number 1. And it says, using a graphing calculator, construct the scatter plot of this data set. Include the least squares line on your graph. Make a sketch of the scatter plot, including the least squares line on the axis below. Okay, so I've got my calculator here. Turn it on. Now let's review calculators. We're going to enter, let me scroll down here, this data set into the calculator. So, first things first, when you turn it on, clear the home screen. Then go to y equals. Make sure there's nothing there. Arrow up here and turn plot 1 on. First step. Arrow back down. Now we're going to, has to be on to graph statistical bivariate data. Bivariate meaning two variables. So then we go to stat. Edit is number 1, so just hit enter. And our L1, L2 should be clear. If they're not cleared, there's 2 ways we can do this. We can go to stat and go down to 4. And then enter L1, comma, L2. Those are the 2 we're going to use. So if there's something in yours, you clear the list L1 and L2 and hit enter. It will say done. And then when you go to stat edit, it will be blank. The other way you can do it is arrow up, press clear, arrow down. All right, so we're going to enter this data. So here we go. 20, 21, 22, 23, 24, 25, 26, 27, 28, 29, 30. I always go to the last entry and count how many entries I have, and this says there's 11, and I check. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Very good. Arrow over to L2 and put these values in. This will take a little bit longer. 3 decimal places. 100.125, 100.145, and look what the calculator is doing. Just because of space, it's rounding to the 10th, but it's still considering it 0.145. Okay, 100.215, 100.239, 100.266, 100.290, 100.319, 100.345, 100.374. Okay, go up. Delete that. Arrow up. And make sure you have the same number of L1s as you do L2s. There's 11, we are good. Or else you get an error mismatch. Okay, so now that's done. Now we're going to generate the least squares line. So you press stat, calculate. Linear regression is number 4. You want your X list to come from L1, your Y list to come from L2. If that already says that, you just enter through. You don't need to put anything in for frequency list or storing reg EQ, and hit calculate. And it creates the equation. It finds the best rate of change and the best y-intercept for our best fit line. Now we want to copy and paste these into y equals. Copy and paste, you go to y equals, your plot is on, y equals, there's nothing here. You press the vars button. You press 5 for statistics. You arrow over to EQ, and number 1 is the regression equation. It just pasted that equation into here. So if I scroll over, there's the number 0.24918 repeating, and the X is right here, plus our constant of 99.62, and it goes on and on and on because it doesn't round. Now if I just hit graph, you won't see anything. Our data starts at, our X starts at 20. This is only going to 10. 20 is way over here. We have to adjust our window. To do that, you press zoom and number 9 for stats. So there's our data. It looks like a really nice straight line. There's the best fit line going through it. Now what we're going to do is create, let me switch pages. So there's the graph there. Using a graphing calculator, construct it and now plot. So we're going to plot these values. So let me bring the table over. It's easier to do it. Well, I could do it from my calculator table. Okay, so if I just go to stat, edit, I can see my values. So this will take a little while, but we need to do it because they're asking us to. All right. I'll use red. First number is 20, comma, 100.13. Here's 20. 100.15 is here. 100.10 is here. This would be 12.5. 100.13 would be about there. 21 is here. That's 100.15, which is here. 22 is 100.17, which would be about, let's see, 17.5 is here, so just underneath that, right there maybe. And then 23, 100.19, just under to 20, right there. Try that again, right there. 24, 100.22. 22.5 is the next line, so let's say about there. 25 is 100.24. Just under the 25 line, right there. 26 is 100.27. 25 is here. 275 is there, so it'd be just under there, right there. Okay, now I need to move my cursor down to see the rest of these. So we stopped at 26, so I want 27. Go to the end of the line. So 30 is my last one, so I'll stop right there. So right here at 27, 100.29. 100.29 is just under 100.30 right there. 28 is 100.32. 100.32.5 is the next line, so it's there. 29 is 100.35. 29, 100.35 is right on that corner, that intersection. And 30 is 100.37, which is right about here. So there's the graph. And then we drew the regression line. There it is. They drew a line through it. It says, using the graphing calculator, construct a scatter plot of this data set. Include the least squares line on your graph. So now we're going to put a least squares line there. I will use a different color so we can see it, and I'll make it thin so it's not covering it. So our least squares line, I may have to move this. I'm just trying to copy this here. It went just a little below that top line. So I'd say maybe like right there. And it went just a little below the bottom one. Okay, so there it is. There's our graph, there's our least squares line. Number 2 says, using the calculator, construct a residual plot for this data set. Make a sketch of the residual plot on the axis given below. Okay, so residual plot, we need to go to second stat plot. We're going to leave our initial plot on number 1. We're going to arrow down to number 2, press enter. It's off right now. We want to turn it on. We want it a scatter plot, so we're going to leave it that. We want X list coming from L1, but we want our Y list coming from the residual. In order to get residual, we have to press second stat, which is list. So we're going to go to second stat, and instead of L2, we want resid. So we're going to press 7. Now we're taking X from L1, and Y is going to be the residual. So the calculator is going to take our L2 and subtract our actual from our predicted. It's going to figure those distances out for us all in one fell swoop, and then it's going to graph them. So here's the graph. Okay, but what I want to do now is go to Y equals, that was our original graph, arrow over, press enter to turn off that equals sign, turn off plot 1, and now we're going to just plot 2 and hit zoom 9 for statistics. Okay, so if you need to back that video up and follow those steps again, please do so. So now we're going to graph this. I'll use green points this time. Okay, so if I want to have a scale, like they're showing here, all I have to do is hit trace. So trace is right here. So if I press trace, it will tell me the X and Y value of this point. So it's X is 20. So we want to break this. Hello. Oops. Undo. There we go. Try that again. We want to put a little break here, showing that the graph does not start right away. And our first point is 20. So I'll put 20 here. The Y value is 0.006. And that point over here looks to be about the same. So we're only going to go up to 0.006. And I'll put 0.003 here, and then 0.001, 0.004, 0.005. Okay, so 20 ended up being, I'll use blue for the dots, ended up being 0.006 approximately, so I'll put a dot there. And then if I just arrow to the right, it takes me to the next point. 21 was 0.001. Okay, so let me just do my scale here so I'm not switching colors over and over and over. And I'm running out of room, so I'll skip every other. 25, 26, 27. And how far are we going out? 30. So 28 would be here, 29 would be here, and this would be 30 and 31. Okay. Now we want to plot those. So since I'm at 30, it's 0.0058, pretty close to 006. So 30.006 is about there. And I'll just work backwards now. 29.0017, just 0.001 is here, 0.002 is here, 0.0017 is just below 0.002. Arrow left. That, when that comes up, 7e -4, that means 0.0002 7. 4 decimal places. That just means a number really close to 0. So we're going to put 28 way down here, right near the 0 x-axis. Arrow left, and now we're at negative 0.003. So I need to do my table below. 1, 2, 3, negative 0.003. 1, 2, negative 0.006. Okay, so we have 27, negative 0.003. 27, negative 0.003 is here. 26, negative 0.002. 4 would be about here. 25 is negative 0.004, which is about here. Let's say down here a little. It's lower than this one. And then 24, negative 0.003 is here. And arrow left, and 23 is negative 0.0027. Okay, 23, negative 0.0027 is not quite 0.003. That's right there. Arrow left. 22 is a positive 0.0012. So 22, positive 1, and a little more. Right about here. 21 is 0.001, so it's right next to it. So we're right about there. Okay, so there's our scatter plot. Number 3 says, do you see a clear curve in the residual plot? Okay, well, it's very clear that this is a curve. So the answer is yes. What does this say about the original data set? Okay, so the answer is yes. There is a clear curve in the residual plot. This indicates a nonlinear curved relationship between volume and temperature. So this linear regression is not the correct regression to use. Since this is a curve, it's either exponential or quadratic or something other than a straight line. Okay, page 5 brings us to the end of lesson 18. Review the lesson summary and go to your problem set.